CAP décollage.
Launched by an Ariane 5 rocket from the Kourou Space Center in French Guiana, the James Webb Space Telescope was designed to answer major questions in astrophysics, such as the formation of planets and exoplanets, the first galaxies in the universe and their first stars, as well as the composition of the atmospheres of extrasolar planets. During the journey, the deployment of the 6.6-meter primary mirror is a delicate and unique operation. Its huge 5-layered sunshield, the size of a tennis court, allows the telescope to cool down to around 50 Kelvin. After a cruise of 30 days, Webb reaches its orbit around the L2 Lagrange point, 1,500,000 kilometers away from the Earth. This is a stable and cold environment, which are the necessary conditions to observe infrared radiation with unprecedented sensitivity. Webb is equipped with a series of 4 instruments located behind the primary mirror. The MIRI instrument is composed of a camera and an integral field spectrometer, both observing in the mid-infrared between 5 and 28 microns. The optical system of the camera, designed by the French team, is made of 5 mirrors and a filter wheel which selects the infrared radiation. The images are formed on a detector cooled down to a temperature of 7 Kelvin or minus 266 degrees Celsius. The study of exoplanet atmospheres, planets orbiting other stars than the Sun, is one of the major objectives of MIRI. For that purpose, it uses 2 different observing techniques. The first is a new technical innovation called phase mask coronagraphy. The coronagraphs of MIRI consist of a mask located at the entrance of the instrument and a diaphragm placed in the filter wheel. The objective is to attenuate the light of the central star to observe the very weak signal emitted by an exoplanet, similar to the principle of a solar eclipse. MIRI will be the first instrument in space to implement this type of coronagraph. This technique allows us to observe young and warm giant planets orbiting at several astronomical units from their star. The second technique is the infrared spectroscopy, observing the transits of planets with short orbital periods. With this technique, MIRI can record the light from the star filtered by the planet's atmosphere as it passes in front of the star, or the light emitted by the planet itself before it eclipses behind the star. The obtained spectra contain valuable information on the planet's effective temperature, the molecular composition, and the presence of clouds. While gas giant exoplanets will be the primary targets of MIRI, it will also be possible to detect small rocky planets with this technique. Thanks to the capabilities of MIRI and the Webb telescope, researchers will be able to better understand the formation of exoplanetary systems, as well as the physical and chemical characteristics of their atmosphere, and perhaps even begin to study the conditions of habitability on these worlds far from our solar system.